In this video, I will discuss the basics of ANOVA. First of all, the purpose of doing ANOVA is to compare 3 or more means, or to compare 3 or more groups. So our null hypothesis when doing ANOVA is null hypothesis all the means are equal versus the alternative that at least one mean is different. I always like to think of this as the Sesame Street alternative because when I was a kid there was a segment on the show where they broke the screen up and they always sang that song, "One of these things is not like the other." So if I think of it that way, I never forget how to do the alternative hypothesis. ANOVA stands for Analysis of Variance. It basically compares the variation within the samples to the variation between the samples. So if you look at these two sets of box plots here, in the ones on the left, they all have tall boxes, which shows that there's a lot of variation among individuals within each group. With this much variation among the individuals, it would not be surprising if another set of samples gave quite different sample means. So the observed differences could easily happen just due to chance. Now if we look at the boxes on the right side, they have the same centers as the ones on the left, but the boxes themselves are much shorter, meaning that there's much less variation among individuals in the same group. So it's unlikely that any sample from the first group would have a mean as small as a sample from the third group. So because the means are far apart and the variation within the group is small, then it's more indicative of a real difference among the means of the three populations. So ANOVA, what that's going to do is it's going to compare these. It's going to look at how much variation within the group and compare that to how different the different means are between the groups. There are two basic requirements for doing analysis of variance. First, the data for each group needs to be normally distributed. We can check this by doing a QQ plot of each sample. And if there's not any obvious departures from normality, we can feel pretty good about the normality assumption. The second condition is that the populations have to have the same variation. Now, obviously, we're not going to know what the population variance is, so our rule of thumb is to look at the sample variances, and if the largest sample variance is less than 4 times the smallest sample variance, then we're going to conclude that it's reasonable to assume that the population variances are the same. Alright, so let's look at an example. Which color attracts beetles the best? An experiment was conducted to see what color attracts insects the best. 6 boards, each of 4 colors, were placed randomly in oat fields. The boards were covered with a sticky material, thus trapping insects that came in contact with the boards. The number of insects trapped on each boards was recorded. So we were comparing 4 groups here, basically the 4 different colors of boards, blue, yellow, white, and green. And we want to know, are the mean number of beetles for each of these trapped on each of these boards if they're different. So null hypothesis is that the mean for the blue board is equal to the mean for the yellow board is equal to the mean for the white board is equal to the mean for the green board, or in other words, all the means are equal, versus the alternative hypothesis that at least one of those means are different. One of those things is not like the other. The first thing we need to do is check our requirements. The first requirement is that all the populations are normally distributed. To check this, we're going to construct QQ plots of each sample to verify normality. To create QQ plots in Excel, the first thing I need to do is open up the Quantitative Descriptive Statistics Excel file that we've been using all semester long. So this brings me to the main page, and there's a QQ Plots tab along the bottom. So I'm going to click on the tab for QQ Plots, and the first thing I want to do in here is I just want to clear out the data that comes preloaded in there and get this all ready for the new data that I want to put in there. Not sure what that error is all about, but so now I'm going to go ahead and open up the Excel file that contains my data. And you can see that the first column, board color, contains the colors of the boards, and the second column contains the number of insects trapped. So we said that there were 4 colors and there were 6 boards of each color. So you can see that there are 6 observations for each of those board colors. So one at a time is how I'm going to have to do these QQ plots. So I'm going to start by cutting and pasting all of the data for blue. So I've copied that data. Back in here, I'm going to paste that data. Once I've pasted the data, I need to sort the data. So I'm going to highlight the whole column. I'm going to click on the Data tab. Then I'm going to click on Sort and make sure it says my data has header rows and click on OK. And now I've got my QQ plot for blue. I'm going to repeat this process for all of the other colors. Here are the QQ plots of all 4 samples. And what we're looking for on a QQ plot is just to see if the points fall on the straight line. If the points mostly fall on the straight line or kind of close to the straight line, then we would consider the data to be normally distributed. And if there's some significant pattern or curvature going on, that's when we're going to be concerned. So looking at these 4 QQ plots here, they all seem to roughly fall pretty close to the straight line. There's not any like distinct curvature patterns or non-random patterns that we really need to be concerned about. So we'll consider that condition or requirement to be met. The second requirement is that all of the population variances are equal. And to do this, we're going to compare the largest and smallest sample variances. The largest variance should be no more than 4 times the smallest variance. So I'm going to show you how to find the variances later when we get into the analysis of variance in Excel. So for now, I've just taken all the variances and put them into this table for analysis. The smallest variance was white with 14.167, and the largest variance was yellow with 48.267. If we take 4 times 14.167, that equals 56.668, which is more than 48.267. Thus, our requirement that we have equal variances has been met. Now that we've checked the requirements, we're ready to go ahead and begin the analysis of variance. The first thing you need to do is open up the Quantitative Inference Procedures Excel spreadsheet. And we want to do analysis of variance, so we're going to click on the tab at the bottom that says ANOVA. So now that I'm here, first want to clear out all of the data that just comes up automatically when you open up the program, just to get everything out of there. So I'm going to clear those contents, and that's going to get it all ready for the data set that I want to put it in there. So my data set is here. I have one column that contains the board color, blue, green, white, or yellow, and the other column that contains the number of insects that were trapped. So as mentioned previously, there were 6 boards of each of the 4 colors that were placed out in the fields, so I have 6 observations for each color. So I'm going to copy each of these color by color over into my Excel ANOVA file. So I'm just going to copy, starting with the blue, copy that, and put it over into column 1. I'm going to change the name of that variable to blue. Then I'm going to go back and do the same thing with all my other colors. So I have green, copy that, paste it in, change the name. I'm going to go do it for my next color, white. And finally, I'm going to do it for yellow. Now I've got all my data in, and now you can see that over here on the right-hand side in Excel is all kinds of really great information. So let's go ahead and take a closer look at the output that Excel gives us. First, we have the degrees of freedom. Now in analysis of variance, there are 2 kinds of degrees of freedom rather than just one like we've been dealing with the t-distribution. So in this case, there is a between groups degrees of freedom and a within groups degrees of freedom. So we say that we have 3 and 20 degrees of freedom. Next we have our test statistic. The test statistic is an F test statistic. In this case, it has the value of 45.045. Next, we have our p-value, which is the thing that we're most excited about that's going to help us draw the conclusions about this test. And in this case, we have a p-value that's really close to 0. Excel starts using exponential notation as the numbers get really small. So this is really 4.4 times 10 to the negative 9th, which would be an extremely small number there. In addition, in Excel, we also get all these descriptive statistics. So for each group, we have the mean, the standard deviation, the variance, and the sample size. And these variances here in this box, these are the variances that you would use to check the requirements. These are the same ones that I used previously in this video to check that variation requirement. As part of our analysis of variance, one thing that we want to do is create a graph that will help visually depict our data. And a good graph to compare groups for a quantitative variable is Boxplots. In this case, we'll have one box plot for each of the 4 different board colors. So to do that in Excel, first thing we're going to do is we're going to highlight the data that we want to construct the box plot for. Once I've got my data highlighted, I'm going to come up to the Insert menu and I'm going to click on Recommended Charts. I'm going to click on the tab in Recommended Charts that says All Charts, and several ways down here there's the option for a box and whisker plot. And look, it even kind of shows it to me there in many forms. So I can click on OK, and ta-da, there is my box plot. Now, of course, Excel didn't read my column headers and make the boxes the same color as the boards. But since this is Excel, we really can just kind of click on things and it'll allow us to customize them. So if I just double click on that red box there and click on the little paint thing, change the fill color to green, since that was my green boards. And then I'm going to click on this next one. This one was white. I don't know if white's going to work that great, so I'm going to do like a kind of a light gray color to represent white there. And then lastly, I had yellow, so I'm going to go ahead and change that color to yellow. And I'll close out my edit window and look back at my chart, and it almost looks perfect. I'm not sure what happened with this first one here, so I'll go back in and see if I can paint that the color that I wanted again. Please be green this time. Thank you very much. Okay, now looking at my chart here, then the colors of my boxes actually do match up with the colors of my boards. And looking at my box plot, I can see that blue and white seem to be very similar to each other in terms of the number of beetles trapped on these boards. It looks like green had a few more beetles trapped on the board, and yellow had the most beetles of all trapped on the board. So looking at this box plot, it definitely looks like there is a difference between the groups, which is exactly what we saw with our analysis of variance F test. So after all this, what should we conclude? Well, recall that our null hypothesis was that all the means were equal, and the alternative was that at least one mean was different. Our p-value was essentially 0, and we all know that if p is low, HO must go. That means we're going to reject the null hypothesis, and we have sufficient evidence that at least one mean is different. And based on our box plots, we can pretty safely conclude that yellow has the highest amount of attraction for those beetles, green second most, and blue and white are the least and seem to be not very much different from each other. So what kind of action should you take? Well, be careful if you're wearing yellow next time you go into an oat field.